So how, if we're talking about rotational dynamics, differ from rotational kinematics? What's kinematics? Stumped you already. Kinematics is just the description of the motion. It's the measurement of the motion. Dynamics, though, refers to what about the motion? Well, what's actually making the thing move or change its movement in the first place. So in terms of linear motion, kinematics is speed-time graphs, equations of motion. In terms of rotational motion, we're dealing with angular equations of motion, and also, instead of force, what's the thing that makes something turn? That sort of twisting moment. What was that called? A torque. So to make something actually turn or to slow it down in terms of rotation, you apply a force perpendicular to the center of the motion. So if something's rotating like that, that force multiplied by the radius, the force is usually either applied perpendicularly or as the perpendicular component of the radius times the torque, which has a Greek symbol tau, is equal to that force multiplied by the radius. So if the torque is force multiplied by radius, what would the units be for torque? Jonathan, what would be, if we were multiplying newtons by meters, what units would you have for torque? Newton meters, okay? So Newton meters are the units for torque. And an easy example would be to work out the torque that it needs to open a door. So you pull the door with so many newtons of force, the radius of the door to the handle is so many meters, and you can work that out from there. So that's what torque is. That's what makes things move around. Now, if we think about something which does get spun round, say the turntable here, there's two ways you can make the turntable spin round. The first one is apply a torque at the rim of the thing that you're trying to turn. It's much easier than if you apply a torque further down at a smaller radius. So that gives you an idea that the same force applied at different radii gives you different torques. But if we do apply a torque to this and make the thing speed up, so if I tie this around the middle here, I'm just going to wind that up like that. So Anna, seeing as you missed out on this last week, you get the chance to spin the turntable. So if you're going to just apply, say, 2 newtons of force there. So, okay, will that zoom in at all together? Okay, ready? So Anna's going to apply 2 newtons of force there. And we're seeing quite a slow angular acceleration. Okay, that's fine, thanks. Now if we do the same thing, instead of around a small radius, if instead we put it around a much bigger radius up here, what do you think would happen to the angular acceleration if you're applying the same force, bigger radius? What will that mean about the torque which you're applying? Same force but a bigger radius. Okay, Gregor, what do you reckon? Yep, okay, so if we wrap that round there like that, and again, Anna, if you just pull with 2 newtons, so you're ready, hang on, 3, 2, 1, go. We're getting a much bigger angular acceleration. If it was wrapped round like that and you kept applying 2 newtons, the thing would give you a much bigger angular acceleration. So the angular acceleration is related to the torque. There's also something else that we thought about, and that's to do with this sort of amazing bar that, for those of you who weren't at Harriet Watt on Monday, had a chance to go with. What were you able to change about the bar on Monday? Okay, yeah. So this distribution of the mass across the bar, and that can give you a difference in the angular acceleration as well. So we found out that changing the torque will change the angular acceleration. If we use a couple of masses on here with the bar at different heights. So we start off with the bar close in. So it's the same mass on this bar, but with the masses close in. You can, well, something that you will be doing is measuring the angular acceleration there. So it'll start to accelerate quite quickly there. And within just a few seconds, you're getting high omega. If we make the distribution of the masses much greater, so increasing the radius, what would you expect to see happening in terms of the rate of angular acceleration? Oops, healthy. Okay, so if I let that go now, got a very slow increase in angular velocity. So the angular acceleration is much smaller. We're applying the same torque, it's the same force multiplied by the same radius here, but we're getting a much smaller alpha, a much smaller angular acceleration. Very similar to if you're trying to move something in a straight line. Okay, so if you've got something, say this trolley which you're trying to accelerate, so you apply a couple of newtons of force to that, it will accelerate. What two ways could I increase the acceleration of this trolley with Stas's wheels on it? Yeah, if you put 4 newtons on, as you know from standard grade, the bigger the force, the bigger the acceleration. What else could I change about the trolley which would give a bigger acceleration? No. Okay, if you take the mass off, going back to the original 2 newtons of force, lighter trolley, you get a much higher acceleration. That much you've certainly investigated at standard grade. Changing the mass, its distribution across the bar, you'll be investigating later on this morning, I would hope. So this is all tied up with really a rotational version of Newton's second law, because Newton's second law has the mass here, the force and the acceleration are all tied up with F equals ma. You can relate torque and angular acceleration by, well, it's more than just the mass. As Alistair pointed out, it's not just the mass, it's the distribution of the mass. So we need a constant in the equation, which is the moment of inertia of the system. And the moment of inertia is to do with the mass and its radius from the center. So that's the thing that we're going on to. Anyway, so we just add in underneath here, if you haven't already got it in your notes, about Newton's second law for rotational motion. So if you've got a mass which is rotating around a circle, there's the radius r, it's got a torque applied to it, tau, which could be equal to force times radius. And it's got an angular acceleration of alpha. Now, alpha, remember, is the rate at which omega is increasing, not the central acceleration. And the three things are related by tau equals I alpha. Tau is the torque, that's in Newton meters. Alpha is in radians per second. I is the moment of inertia. The moment of inertia is defined for a point mass at a radius as being the mass times the radius squared. So what would the units be for moment of inertia from that law? Yeah, so you've got kgm squared. And so for a point mass, you've got, so this is now moment of inertia. So just a single mass with a light string. So for instance, if you had a bit like the thing that you were whirling around the other day, going around like like that, the moment of inertia of just a single mass with very little connecting it, so we're assuming that the mass of the string is much less than the mass of the bung. In that case, the moment of inertia I is equal to m r squared. That's for point mass. For a disk, if you've got the mass distributed, so capital M for the mass of the whole object, and if a disk has got the mass all around it, so this would be something like the turntable here, where you've got a wooden disk there rotating around a center there. The moment of inertia for a disk is equal to half mr squared. So different objects have different moments of inertia. If you take the moment of inertia for a rod or a long beam like this around one end, its moment of inertia is different to the moment of inertia when it's spinning around that, because the distribution of the mass around the center is different. Similarly, if you've got a football or basketball spinning, that's got a different moment of inertia because it's a sphere as opposed to a disk. There is one other object which has a moment of inertia equal to mr squared, where you take the mass of the object and the radius squared, and you'll get the moment of inertia, even though it's not just a point mass. What would have all of its mass distributed at a radius r away from the rotation? Chris? Yeah, so a hoop or a bike wheel, if you've got something which has got all its mass distributed at a radius r, the moment of inertia of a hoop or a wheel is just mr squared. So all these things have got their own particular moment of inertia, and the only one that you need to know in advanced higher by heart is just this one that I've got the box round. All the other ones you would be given if need be. So don't go away thinking, oh, I've got to learn what the moment of inertia for a rod or for a sphere and all these things are. You'll be given them. All you would need to know is what the mass is, what the radius is. If you've got a combination of things, if you've got, say, mass on a disk like that, you can add the moment of inertia mr squared for the mass, add it to the disk. If you've got a wheel which has got heavy spokes, you can add the moment of inertia of the spokes onto the moment of inertia of the hoop. So moment of inertia can be added up. All the time, though, because you're multiplying by mass by meter squared, the units are kg m squared. Your equation T equals I alpha, as I say, it's just Newton's second law of motion, but this is giving you the angular acceleration.